want to try and develop a real good understanding of the chain rule and why it works the way it works. So I'm going to take us all the way back to the very first week of class. And here's a curve. We're going to call that function f. And I'm going to mark a point here. I'm going to call this point x1, and I'm going to call this point here x2. So on my function, on my curve right here, I have 2 points. I have x1, comma, y1, and I have x2, comma, y2. And if I draw a line through those 2 points, I can calculate the slope of that line. Now, I want you to remember something. Derivative is the same thing as the rate of change, which is the same thing as the slope of the tangent line at any particular point. This is really important to remember and understand. So, if I'm calculating the slope of the line, just the way I did way back in middle school, I go y2 minus y1 divided by x2 minus x1. What's that saying? That's saying the same thing as the rise over the run. But what it's really saying is that for every change, this delta means change in my x value. So every time my x value changes a little bit, I'm going to have a change in my y value, the rate of change. It's going to go up the function a little bit. That's the rate of change. And it's also the slope of the tangent. So you can kind of see slope of the tangent, rate of change, derivative, all the same thing. Well, I'm going to make a couple of changes here. Instead of calling this y1, since my function is f, I'm going to call this x1, comma, f of x1. And I'm going to call this x2, comma, f of x2. So this is using our function notation to indicate that to get a y value, I take an x value, plug it into the function, and I get a y value. And then I'm going to change it even a little bit more. I'm going to say this point right here is just x. And this distance between these 2 points, I'm going to call it h. So this point is x, and this point over here is x plus h. So now my points are labeled x and f of x. And this one over here is going to be labeled x plus h, comma, f of x plus h. And when I go ahead and I kind of go back to my slope function, now it's going to look like this. It's going to look like y2 is now that. So it's going to look like f of x plus h minus y1, which is now f of x, divided by x plus h, which is my x2, minus x. But notice something, and this is probably beginning to become a little bit more familiar. Here, I have x minus x. So those are going to go away. And what I have is I have f of x plus h minus f of x over h. That is the slope of the line. That is the slope of that tangent line right here. Now, if I start moving my x plus h closer to x, I start getting really, really, really close. And as I do that, this point here starts to come down the function line. And if I do that until h is essentially gone, h becomes 0, I have the limit as h approaches 0 of this, which is our derivative. It's the derivative at a single point. And the beauty, the magic of this whole thing is that it used to take 2 points for me to calculate a slope. But now, using the concept of limits, I can calculate the slope at 1 point on a curve. And that is our rate of change. So let's take a look at the sine function. This is a nice function to describe this with. And if I look at the sine function, you're going to have to follow my little arrows here. But when I look at the sine function, excuse me, right in this little area right here, very tiny area. So right at the origin. You can kind of see that my slope there is 1. Now we know that the derivative of the sine function is cosine. And we know that the value of sine at 0, that's theta, I want to make it 0, at 0 is equal to 0, but the value of cosine at 0 is equal to 1. So if I go back to my graph right here, I'm looking at the slope of the line right there as sine is 0, and that slope looks pretty much like 1. Let's zoom in on it a little bit just to see it more clearly. So I'm going to zoom right in here. I'm going to zoom in a lot. And I've changed my scale to make it look, excuse me, to make it even, make it square. And you can see very clearly that as I'm in really, really small numbers here, my slope of the sine function is 1. Well, let's look at the slope of sine 2x. So here's sine 2x, I just made it in blue, and it seems pretty clear that the slope of sine 2x right around 0 is 2. See, I go over 1, up 2. Over 1, down 2. As opposed to my sine function where I've gone over 1, up 1. Over 1, up 1. Over 1, up 1. So right around 0, it's very clear that the slope of the line of sine x is 1, and the slope of the line sine 2x is 2. Well, let's take that back to the derivative and the chain rule. So if I have y equals sine x, I know that the derivative of that is cosine x. If I have y equals sine 2x, somehow I have to account for that too. So the derivative of sine 2x is equal to cosine 2x times 2, the inside function. This is my outside function. This is my inside function. It's this 2 that is making the difference here, and why I have to use the chain rule in order to account for these changes in slope. This 2 right here, as we can see again in the graph, I'm going to go back to a larger. As you can see in the graph, that 2 right there really increased the slope. In fact, it doubled the slope of the sine function. And since the slope is my derivative, it doubled my derivative. So I have to use that inside function to account for that change that it's making.